Hello. In this video, we're going to be looking at force analysis part 2 and talking about center of mass. And if you click on the link here um, up here, there's actually a link to a scene from the movie Gravity, and you can look at that carefully and see if you think that the what their film is actually following Newton's laws or not. But So as I said, we want to talk about center of mass. And so here's the definition of center of mass from Wikipedia. And you can see that it says this is the point to which a force may be applied to cause a linear acceleration without angular acceleration. So I guess if you think about it, like if you think about this pen right here, or say I had it on a table, if I put a force on the end, it will it will move, right? I mean, the center of mass will move, but it will also start to rotate. But if I apply the force right at the center of mass, then it will move linearly, right? It will not, there will be no angular acceleration. Or another way to think of it is it's just if you have some body, a system, and that point, assuming that the system is rigid, that point where all the weight could be considered to act. So obviously, if you could apply a force there and it was, in some gravitational field, you could balance it at that point because all of the weight is essentially acting through that point. So what are the conditions that we might apply to determine where the center of mass might be? So I'm just going to draw, suppose we have, just going to draw kind of a schematic of a robot here, and maybe we have some wheels here, and we have, let's say we have a couple of weights of some different systems. Maybe this is 10 pounds here, and maybe we have another weight here. We'll call it, say that's 40 pounds, right? Maybe we have some weight, some system out here, and maybe that weighs 20 pounds, okay? So if we wanted to determine what the force is on the wheels here, the normal force, so maybe I'll call this, I'll call it FL, and this force over here, FR, left and right, okay? And so we know that in a free body diagram, of course, you need to have distances. So let's say that the distance here, let's say that this is 2 feet between the wheels. This one is right over the wheel, and this is 1 foot right here. And let's say this is 2 feet right here. Okay, so we would be interested in knowing the center of mass of this system for a couple of different reasons. One, if we knew the total weight and we wanted to solve for F sub L and F sub R, the normal forces on the wheels, maybe the front, the wheel on the right is a driven wheel, or the wheel on the left, and you end up pushing up against something else. So you want to be able to simplify the different weights of your components, different parts of the robot, into a single weight acting at a single point. So the question is, what are the conditions? In other words, if we want to replace the 10, the 40, and the 20 with just a single force, what are the conditions that it must meet? So the 10, the 40, and the 20 are parallel forces. So you think of it this way. We have a system of parallel forces. We want to replace them with just a single force. So if we think about it, it would make sense that, first of all, of course, the sum of the original force system must be equal to the resultant force, right? So back here we had 10, 40, and 20, and so that adds up, what, to 70 pounds. So whatever the resultant is, and let me change color here if I can. So I'm going to say, this is the force that's going to be our resultant force, R, and it has to equal the sum of the original forces. So that's just summation sign of the original forces. And we can see that for this problem, that's 70 pounds. Okay? But in order to, for this resultant to create the same reactions at the wheels, it depends on where it's placed, right? And so in other words, the wheels, the forces on the wheels have to be exactly the same, whether we just put in the 10, the 40, and the 20, or we just replace them all with a resultant. If that's not the case, then it doesn't act through the center of mass. I mean, it has to be able to create the same effect on the body as if we had the distributed forces. Okay, and so what we have to do then is place R so that it has the same moment, and I'm just going to say, let's say that that's X bar. So this distance, and we'll measure from the left wheel. You don't have to measure from the left wheel to do this. You can measure from any point, but the moment created by R, so what we're saying is that the moment created by R about any point, we'll call it any point P, has to equal the sum of the moments of the original system about that same point. Okay, so if we use the right-hand rule, of course, about point L, so we're going to say the moment of R about point L is just going to be equal to what? Negative, right? Because we go by the right-hand rule. The moment arm is X bar, so it's going to be negative R times X bar, okay? And that has to equal the sum of the moments of the original system about L, okay? So the 10-pound force is right over L, so it doesn't create any moment. And then we have 40 pounds times 1 foot. It's also a minus, right? 40 pounds times 1 foot. And then we have the 20 pounds, and its moment arm about point L is 3 feet, right? 1 foot plus 2 feet. So that's going to be minus 20 pounds times 3 feet. Okay. Now notice that this isn't, we're not summing the moments and setting them equal to 0. We're not looking to set moments to 0 here. We're looking to replace a set of forces, excuse me, with another force. So we want them to be equivalent. So anyways, if we go through and solve this, right, what we want to solve here for is X bar, right? And so we have 40 times 1 is 40, 20 times 3 is 60, so that's 100. It's 100 foot-pounds. And then we have to divide by the total weight, which we said was, right, 10 plus 40 is, and so that's 70 feet. I'm sorry, 70 pounds. 70 pounds. Okay? So you can see that the units cancel out, and we're left with feet, and we're left with, we'll say 10/7 of a foot, right? So what we know now is that if we place a 70-pound force on this robot, 10/7 or 1 3/7 feet from this axle, then the forces on the wheels will be exactly the same. Okay, forces on the wheels will be exactly the same. Okay, so why don't we solve for that? In other words, so now we will do the equations of equilibrium, and so first of all, there are no forces in the x direction, so we'll just sum the forces in the y direction. They have to add up to 0. So we have F sub L plus F sub R minus 70 pounds, right? And well, let's just sum the moments about point L again. So now, and these do add up to 0 because now we're doing the equations of equilibrium. So we have sum of the moments about L equals 0. And so what do we have? We have F sub R, right about point L. That's creating a positive moment, right, counterclockwise. So we have 2 feet times F sub R. And then we have minus R, which is 70 pounds. And its moment arm, we calculate, is just X bar, right? So that's 10 over 7 feet. 10 over 7 feet. Okay, so now we can go ahead and solve this for F sub R, right? These have to sum to 0. So we'll just do the algebra, and F sub R is going to equal, right? We bring the 70 on the other side. So let's see, we have what? 70 times 10 is 700, divided by 7 is 100, and then that's divided by 2 feet, and so we end up with 50 pounds here. Okay, and then from the top equation, we can write that F sub L, right, they have to add up to 70, so this is 20 pounds. Okay, so again, the principle was that we wanted to replace these 3 forces, the 10, the 40, and the 20. They're parallel forces. We can replace them with a single force, a resultant force, which is just going to be equal to the sum, right? But it has to be placed so that it creates the same moment about any point. We're free to pick any point we want. It doesn't even have to be on the object. But the R, the resultant force, has to create the same moment as the original 10, 40, and 20. Otherwise, it's not creating the same effect on the body. Okay? And then once we have that resultant, we can then do the free body the equations of equilibrium and solve for F1, FL, and FR. Now, we could have done that without replacing the 10, the 40, and the 20. But it's nice to have it, worked out. If you have a robot with certain components, it's good to have the total weight and where the center of mass is so that you can quickly determine things like, for instance, is it going to tip over? If you add, if we add an arm with some other weight out to the right, then we need to be able to determine if it's going to tip over. We can tell that with this particular loading, even though the 20-pound force is out at the end, right? The location, X bar, was 10/7, right? Or 1 3/7. So the resultant of these 4 loads was in between the 2 wheels. So that means it's going to be stable. It's not going to tip. If the resultant turned out to be outside what we say the polygon of contact, in other words, where it's being supported by the ground or the floor, right? If the resultant is outside of those, then it will tip, right? Because then you would have some net moment about either wheel, and unless the other wheel is on some track so that it can pull, so that a force can pull down on that wheel, then it's going to rotate. It's going to tip over. Okay, so again, the resultant force has to equal the sum of the original system, and it has to be located such that it creates the same moment about any point as the original system. So what I want you to do now is you have the handout for Force Analysis 2, and I want you to try this example. So first, you have a robot here, a robot base that's 80 pounds. It has a lower arm that's 12 pounds, an upper arm that's 10 pounds, and it's picking up a 4-pound ball. So first thing I want you to do is determine the resultant, which again is just going to be the sum of those forces, and then to determine X bar. And why don't you measure? Let's measure from this point here. So we'll just call that point L. So measure everything, all your momentums from that point, and determine the resultant. So in other words, they're going to have some resultant force here, and I want you to determine X bar, right? Where is that located? And then you want to determine the forces. Once you have that R, that force, and where it's located, then it will be easy to determine F sub L and F sub R, just like we did in the previous example. And you have to answer the equation, will it tip or not? Okay, so why don't you go ahead and you have the handout for this, for the sketch of this problem, and then put your answer in the quiz, the online quiz, and then we'll continue from there.